Thank you so much for inviting me here, respected dignitaries. This is a really great honor for me to come here and be able to present some of things that I do at IIT Kanpur, which is mostly related to from micro to nano and how it can be applied to sensing and remediations. So today I will be in fact talking about this fabrication, characterization and application of various nanostructures in sensing and remediation. Part of it was because of whatever projects we had, we developed some technologies which are used for doing sensitive detection of, for example, gases, sometimes also related to how you can do dye removal from water, particularly textile dyes, and a variety of other areas of biological interest where you can do biological sensing, etc. using these nanostructures. In fact, before starting, I would like to acknowledge my student, Dr. Ankur Gupta, who is now a faculty member at ITM University and is soon going to go for a postdoc assignment to US for his valuable contribution. In fact, this work is his PhD work. So, needless to say that I must acknowledge him before beginning. And I would give some basic introduction, followed by some topical topics of interest, and then describe each of the topic to some details, And a purpose of a conference like this, in my understanding, is more interactive in nature, so you should have learning by interaction. So in case you have any questions, feel free to ask me at any time during the presentation. So having said that, I would just like to first introduce that what really I have today. So I will be talking about some of these projects, like development of nanoporous palladium for sensitive detection of hydrogen. Then I'll also talk about a dense zinc oxide nanobundle grown in nanoporous silica template, again for hydrogen detection. A little bit of theoretical modeling, some understanding about how these nanostructures are formulated. We'll also talk about some super hydrophobic polymethylsilicispyroxane modified ZNO nanostructures, particularly for photocatalysis application, for dye remediation, etc. And then some other topics where you see that these nanostructures are utilized for dental implants, they're utilized for biosensing, so for various different kind of activities that you can find out this nanostructure to be incorporated. This is a sort of schematic slide which talks about what is the beauty that nature takes at the nanoscale. In fact, it's a poster which was presented in one of the SEM conferences that we had at IIT. If you look at, on the right here, if you look at the scales are really varying between micrometers all the way to nanometers. And on the left here are more objects which you can see and you can believe, because you are able to see them. Unfortunately, you can't see these structures so easily. And for that, you have to use all sort of processes to be able to interpret about these structures, the way they are formulated, the way they are grown. So this, for example, is a cardoon flower. And this structure here is made of zinc oxide. And it is a nanostructure where these rods which are coming out, or these hollows which are hollow cylinders which are coming out, they're about close to, let's say about 50 nanometers in diameter. And you can grow as tall as about close to a micron. These are again zinc oxide bamboos, which are mimicking the natural bamboo, which you can see here. See the difference in scale. These are some hexagonal plates or bowls, and these are again made in zinc oxide, although at that particular nanoscale. So what you can do with this is basically, because of the fact that the surface area increases tremendously, and owing to that area increase, there are a lot of different varied effects which would come up into picture when you talk about nanostructures. Definitions. And if I look at what are really 0 dimension, 1 dimension, 2 dimensions and 3 dimensional structures, nanostructures. So a 0 dimensional nanostructure has all dimensions in the nanometer range. For example, you have some surfactant within which has a lyophilic and lyophobic group in water, and it gets some kind of an arrangement by itself. So a lot of these are also developed by self-assembly processes. So these are 0 dimensional. If I go to the next level, we have 1 dimensional nanostructure where 1 dimension of the nanostructure is outside the nanometer range. For example, you have nanowires, nanorods, nanotubes, so on and so forth. You have two-dimensional nanostructure where again two dimensions of the nanostructure changes varying between 0 dimensions to 3 dimensions, which almost always happens because of the discreteness that comes at the nanoscale, which is otherwise not available at the macro scale. And because of that, the way that the orbitals are defined, the way that the properties are defined are called as bulk properties. Okay? So in the nanoscale, there would be more discrete behavior of individual atoms because of the size scale, and you will find a complete different physics in most of these cases, which will change many properties, or many improvements would be given to, or iPods, and tablets, where you look at the scale from a perspective of really small, and small is always faster to some extent. A domain like protein and DNA, which can be used for conduction of electrons, and then there can be different arrangements within them so that you can have super fast communicators and also improving the semiconductor material and the way that it behaves. So having said that, if you look at the two basic approaches that we follow in nanoscaling, the one approach is called top-down, which typically means that you have a higher size material and you are selectively materials like thin films, heterostructures, lithographic wire, they are actually made top-down. So you are having a larger structure, and with several processes like it gets translated, which is actually the gene. Okay, so it's not that somebody has constructed the gene. Mother Nature automatically does that. Okay, and this is because of self-assembly processes, which are mostly energy-driven. Okay, and because of minimum energy conditions everywhere, there are going to be structures formulated which are like optimum structures, and that is the essence of learning nano from builds in which you can envision how nano can be laid out. So having said that, let's now go to what we have done or how sensing can be done. So the first topic I would like to present here is a development of a nanoporous palladium sensor for hydrogen detection. And before doing that, I would like to emphasize on two things. Why hydrogen? Why we have chosen hydrogen to be detected? Which can sense, right? Sense what? Sense can be a physical quantity. For example, let's say you can sense temperature. You can sense something like action. And what is being measured? The hydrogen plus ion. Okay, and what is the recognition element? The chemical type. So this way you have to figure out, in fact, if you look at your own constitution, your eyes, your nose, your ears, they are all sensors. Okay. For example, the olfactory membrane, which is there within the nasal constitution of any human being, you know how many thousands of chemical reactions take place within that olfactory membrane? There are in fact hair-like moieties called cilia that are designed you like that. But what is happening there are series of electrochemical reactions within the cilia, within the olfactory membrane, which results in an electron flow which can go back into your brain and give you an impetus that this is a smell, this appears to be pungent. This is a smell, this appears to be sweaty, or a very, very sweety kind of smell which you start liking. Okay. So, again, sensor. So you have all these classified as sensors. So having said that, I think I have given enough introduction about sensors. So how do you classify a sensor, or how do you sort of gas sensing? What normally happens is that there is some kind of a electrical change or thermal change or electrochemical change which is associated with the gas which is present in the ambient condition and that is being sensed. So that is how quickly it can do this response, and how much is the variation of the resistance, for example, or the whatever electrochemical transaction is taking place for that particular sensing, that for example, and with that how much time is needed to reach, and it's gone back. You cannot sense again. Okay, so a sensor should have a cyclic part. That, for example, if I am varying the hydrogen concentration, if the concentration is going high, the sensitivity should change, and then when the concentration goes down again, the sensitivity should be such, or the whatever property you're measuring should be such, evacuate it and then flow these gases together, so that there is an environment made of tailored hydrogen varying between 10 ppm all the way to about 1000 ppm, the argon atmosphere, and vice versa. So you can actually let the hydrogen concentration go down, and you can let the hydrogen concentration build up again. Okay, so these infrastructures you can develop yourself also. With this, actually this analyzer was completely developed by our students, etc., who were there actually in this particular thing. And what we are doing here is that this sensing element, we are measuring the resistance, means like spheres and it would also coat the nanoparticles of PMSSQ which is there in the solution. So in that case, if I am able to demarcate the volatility of the PPG as opposed to the PMSSQ, what will happen is that at a lower temperature, the PPG will evaporate altogether, and wherever the PPG was there will be creating hollows because the PPG has evaporated together. So in this case, what we are doing is the following. Can you go to the next slide? So we are having a film like this, which we have coated, and this is comprised of the evaporation of one of the phases, as you are seeing in this particular cartoon. The PPG...
how zinc oxide protect the bacteria from...
Okay, so basically there is again the oxygen defects are responsible. So there is a O minus basically, which interferes with the regular cycle. Okay, and it basically creates pores within the bacteria or creates lysis, because of which there is some kind of, it basically becomes unviable after some time.
Can we take, apart from the...
But then what happens in zinc oxide, that you have these absorbed oxygen, O minus, which is there on the outer portion of the structure of the zinc oxide.
Sir, is there a detailed mechanism of lysis of the bacteria?
There is. I mean, I'm sure I can discuss it with you in details. Probably I don't have that slide to explain to you as of now, but there is a cycle through which the bacteria gets killed. And in fact, what we have seen is, the first response they will give is, zinc oxide is cytotoxic in nature. So they will kill all the other healthy cells which are there. But that's not true. The ethical committee has made a clearance now. Zinc oxide has been used in dentistry not since today but since 1960s. Okay, in some form or the other. And we are not perceiving that some filling has already been done and the patients have not yet come back. Okay, so when they come back, we will see what is the life, etc. which is there. The other aspect which is there is that zinc oxide produces a harder material because
there's also so many bacteria which infect the urine, and then go for the culture of the or the detection of the bacteria.
Okay, so that is a sort of a conventional thinking. You look at the work of Dr. Suman Kapoor. Okay, she has one aspect is that there are only 2 or more such bacteria which are major, in nature, which would be probably the most positive, in terms of the infection.
From your side, that actually makes. So what are the materials could be used for the photonics? Eventually, I am thinking like that. If you took a equipment, electronic equipment, and put it on inside the water, it could not get affected. So what are the material they could be which you use for the electronics and communication engineering or the electronics?
Okay, so I think one. Okay, so let me tell whatever I know of, and I can probably explain something. So if you look at zinc oxide, it's already used within solar cells. It finds a lot of applications within a lot of electronic platforms. Okay, it's a type material, zinc oxide primarily.